Assalamualaikum and very good morning. Today we will learn about integration by trigonometric substitution. Okay, integration by trigonometric substitutions can be useful in evaluating integral involving radical terms such as square root of a squared plus x squared, square root of a squared minus x squared, and square root of x squared minus a squared. A suitable substitution will eliminate these radicals and evaluating the integral will be much easier. For example, consider substituting x is equals to a sine theta in the expression square root a squared minus x squared. Then we have here, we substitute x with a sine theta, we'll get square root a squared minus sine square theta. So is equals to, you need to factorize a square outside the bracket, will get 1 minus sine square theta. And then you know that using the identity you will get cos square theta. So equals to a cos theta. So this is table for integration by trigonometric substitution. When you have a square minus x square here, so is equals to x equals to a sine theta. So identity used here is 1 minus sine square theta is equal to cos square theta. So when you have square root a square plus x square, x is equal to a tangent theta. So 1 plus tangent square theta is equal to secant square theta. And lastly, when you have square root x square minus a square, so x is equal to a secant theta. Secant square theta minus 1 will be equal to tangent square theta. This reference the table above taken from the Substitution textbook edition page number 5. So you need to remember this table. So look at this.
Welcome to Electroline. In this series of videos, starting with this video here, we're going to explore how to use the technique of trigonometric substitution to solve three very difficult integrations if we didn't use that particular technique. The three integrations are the square root of a squared minus x squared, the square root of a squared plus x squared, and the square root of x squared minus a squared. Now, what we do is we substitute in for x a particular value. In the first case, we let x equal a times the sine of theta. In the second case, we'll let x equal a times the tangent of theta. And in the third case, we'll let x equal a times the secant of theta. Why do we do that? Well, that's what these triangles are for. Take a look. On the first triangle, if we let a be the hypotenuse and x be the opposite side, then the adjacent side becomes a squared minus x squared. That is from the Pythagorean theorem. Notice that the sine of theta is defined as the opposite side over the hypotenuse, which is x over a. So therefore, x divided by a becomes the sine of theta. On the second triangle, we'll let a be this side, x be that side, and then the hypotenuse is simply the square root of x squared plus a squared, and that is again Pythagorean theorem. Notice that by definition, the tangent of this angle is x over a, which is what we find here. The tangent of theta is x divided by a when we plug the a over there. And finally, the third triangle, notice that if we let x be the hypotenuse and a be the adjacent side, then the opposite side becomes the square root of x squared minus a squared. Now we realize that if we take the cosine of this angle, and let's show that here, if we take the cosine of theta, that is equal, by definition, a divided by x. But the secant of theta is the inverse of the cosine, which is therefore x divided by a. Therefore, x can be written as a times the secant of theta, which is what we have there. Those three substitutions for x into our integral will make it much easier to find the integration. And so the objective then always is, when you recognize that you're dealing with one of these types of integrations, and any derivative of that integration, of course, derivatives may be a bad word, but there's all kinds of ways in which we can come up with a situation where this appears somewhere in the integral. In the numerator, in the denominator, multiplied times x, divided by x, multiplied by x squared, and so forth. But in each case, that substitution will allow us to find the integral of those types of integral. Now, on the next video, I'll show you the whole slew of different types of integrals that can be solved by using the simple trigonometric substitution. So on the next video, you can see how many different ways that this can be applied to so many different kinds of integrations that otherwise would be very difficult to integrate. So stay tuned and see how many ways we can apply this kind of thing.
Alright, so that is an example of the video. You can check in the website's YouTube. So
Welcome
next,
to our lecture line. In this series of
we move
videos,
to the example. Evaluate integration of x over square root 1 minus x squared dx. So let x is equal to sine theta, differentiate x is equal to cos theta d theta. So x squared is equal to sine theta square here. So this is a triangle. This is hypotenuse 1, x and square root 1 minus x squared. So equals to integrate of x is equal to sine theta over 1 minus sine theta power of 2 cos theta d theta. So dx is equal to cos theta d theta. Next, use identity. 1 minus sine squared theta is equal to cos squared theta. So sine theta over cos theta square multiply with cos theta d theta. So here power 2 multiply with square root 2, so it's equal to 1. So you get sine theta over cos theta. You can cancel out cos theta over cos theta is equal to 1. So it will leave to be sine theta d theta. And then you integrate sine to be negative cos theta plus c. Lastly, you can substitute back using the triangle here. And then cos theta is equal to negative 1 minus x squared plus c.